Okay, so good afternoon and welcome to the last session of the day. My name's Alan Smith. I work as a Windows Azure consultant for a company called Active Solution. I specialize in training and mentoring and generally evangelizing Windows Azure. So I'm heavily involved with the development community. We've run the Global Windows Azure Bootcamp a couple of weeks ago. We're running the Cloudburst conference again. If you've attended that, we're going to be running that again in September. So I tend to focus a lot of time, focusing on looking at Windows Azure. This session, hopefully it's going to be quite an entertaining session, something a bit different, but also, although we're going to be focusing on looking at video gaming as a scenario, there's a lot of, really sort of serious real-world examples that I'm going to be talking about when we talk about the telemetry data processing side of things. I see working with telemetry and the Internet of Things as being a massive growth industry over the next few years. And I'm going to cover, some of the techniques that we can use Windows Azure for and cloud-based technologies for looking at telemetry. The Xbox One was released a few months ago, and one of the things about the Xbox One is that they're focusing a lot on the community and on live gaming. And last year they were talking about the back end for Xbox One, which is going to be the Xbox Live outfit, which is going to consist of 300,000 servers to actually power all of the back end services that are going to have for the games for people who are playing Xbox One. Now, all of this stuff pretty much is going to be running on virtualized technology in Microsoft data centers, and a lot of this stuff is going to be running on Windows Azure. So it's not 300,000 physical servers, it's 300,000 virtual machines. And because of the way that you can scale the cloud-based platforms, that number is going to be changing continuously as they scale up and down, scale down these services for many games. So that's one of the ways that Microsoft is using its own Windows Azure platform to be able to provide those types of gaming services. When we think about usage patterns for cloud, we typically think about these four distinct usage patterns. You'll have seen this graph in many different slide decks talking about hypothetical scenarios. What I've done here is I've taken real-world scenarios from Alexa.com, actually to show the load that we're getting on websites. So you can see a website for the Olympic Games. You can see the growth of Twitter as they had this rapid growth. You can see Formula One has a predictable burst pattern on it. There's a race going on every weekend. It was the Bahrain Grand Prix. For those of you who saw that, it was one of the best races I've seen for a long time. And we've got a week's break, and then we've got the Grand Prix in China. So the Formula1.com, they can basically predict what the load is going to be on their servers for the rest of this year. And once they know the race calendar for next year, they can predict it for next year as well. BBC.co.uk doesn't have this luxury. For their news site, you can have these unexpected events happening, and this could be happening now. It could be happening in 2 or 3 minutes' time, and you could be having a world-changing event where suddenly, because we've got Twitter, there's going to be 10 times as much load coming on that website. What we're seeing here is the earthquake in Fukushima, and here we're seeing the Arab uprisings in the spring, which is causing more load on the news websites. In some of the actual data centers or the network operation centers, they actually have a TV playing CNN News with the sound turned down. And I was around one of these centers, and we were basically saying, well, why have they got the TV there? Do they watch CNN when they're bored? And he says, no. Occasionally we see a massive growth in internet traffic due to some worldwide event. And we always want to be able to look at CNN and see, okay, why is the network traffic going crazy? Oh, it's because this has happened. How can we plan for that? So that's an important thing that does affect cloud-based technologies. For online gaming, they have a different usage pattern now, which they talk about with launch week. Halo uses the Windows Azure Service Bus, and the most popular time for people using the Halo game and playing the Halo game is the weekend when that game is launched. That's when these sort of real dedicated gamers will take the day off work because a video game is being released, and they'll sit at home and they'll play it 24/7 for those few days. After a while, you get to the position where people have gone on and played new games, but there's always, a group of hardcore gamers who 2 or 3 years later are still playing this particular game. And cloud-based technologies is ideal for this. Scalability scalability works in 2 ways. When people talk about scalability, they always talk about scaling up, increasing capacity, adding servers. We've got to be able to handle more load. Well, in this scenario, they want sufficient capacity to be able to, power the game over launch weekend, but they don't want to invest in buying all of this physical hardware. So their, terms of scalability is, this needs to work on launch week, and then we need to scale down. If we'd have purchased all of these resources, we'd be stuck with them. So we want to pay for the resources that we're using. We want to pay, high usage costs at the beginning, and then just scale down gradually as people, actually roll off the game. And if you're a mobile game developer, you may get a completely different curve. Your launch week may be very small with only a few players, and then when your game suddenly becomes popular, you're going to be getting that increase in demand. So you maybe need a different characteristic there. But again, you don't want to invest thousands and thousands of dollars in hardware and services just to try and anticipate how popular your game is going to be. You may not know how popular that game is going to be. So this is about what is going on in Halo 4 on the Xbox Live. We've got people playing Halo on the Xbox. We've got an app called Halo Waypoint where we can keep touch on what's going on in the games. Xbox Live provides core services like membership, leaderboards, achievements, downloadable content, that type of stuff. And what they've built in Windows Azure is they're using the service bus to actually intercept all of the in-game messages. So the Xbox will be sending messages to the service bus. They can monitor the game statistics, they can monitor people's presence, they can monitor multiplayer games. Also, cheating and banning is done in real time based on monitoring how people are playing the game and how other players react to a certain person playing the game. So if you go into a multiplayer game and everybody starts leaving, you go into another multiplayer game and everybody starts leaving, and they actually detect this pattern occurring. They can maybe actually put a ban on you automatically instead of doing it as a manual process. So improving playability, improving the gaming experience. There's a lot of stuff going on in Halo. Also Hammerfall as well. I've not looked into too much about how Hammerfall is using Azure, but they're also heavily dependent on using these cloud-based services. So if you want to learn a bit more about how cloud is used in gaming, a couple of resources I really recommend. This one is on Channel 9, how Halo 4 is using the Windows Azure Service Bus. And you've got Hoop Samoa, who's one of the main developers around this technology, talking to Clemens Vastas, who is one of the main developers behind the Windows Azure Service Bus at Microsoft and has been for some years. They're talking about the challenges that they had, working with that solution. Also, Katie McCaffrey talking to Hanselman. This is an audio podcast, and this is really good, talking about some of the issues that they had developing this solution. In their testing scenarios, they were actually breaking production service bus architecture because they were putting too much load on it. So they're working very closely with Microsoft to actually, get the service bus actually able to handle the demand that they were going to place on that in launch week. Another of my passions is Formula One. I'm a great Formula One fan, and Formula One really brings us into the telemetry side of things. This industry is basically unique in that they've got millions and millions of dollars to spend on research and development. They've got really critical stuff going on with actually monitoring what's happening in the car, and also millions of dollars is based on. I think they've figured out that 1 point in Formula One is worth something like $10 million when it comes to giving out the actual prize money. So 2 seconds on the track, even half a second on the track during a race can basically mean sort of win or lose for these various companies. So they're investing a lot of money in telemetry data, being able to actually monitor what goes on in the car and be able to make decisions based on what's happening with the driving. So what happens is inside each Formula One car they have a standard ECU, which stands for Engine Control Unit. These were developed several years ago in a partnership between McLaren Electronics and Microsoft. So Microsoft are basically, behind quite a lot of the technology for Formula One. The Atlas telemetry system that a lot of the Formula One's teams used is based on the Microsoft stack. So we have the telemetry data that's really important to the drivers. This is courtesy of Lewis Hamilton, who actually tweeted some telemetry data and got into trouble for doing that. But you can basically see all of the numbers. You've got the speed comparisons between two cars. You've got the actual gear selections here. You can see them going up and down the gearbox and all that type of data that they're going to be processing. If you look at the Formula One car, there are sponsorships. So when I started watching Formula One in the 70s, the Formula One teams were sponsored by cigarette companies. Nowadays, most Formula One teams have a technology sponsor who will be helping them with their actually telemetry processing and with all of the stuff that they need to actually go racing these cars. Two sponsors here. Here we've got Microsoft Dynamics. So Microsoft is actually sponsoring the Formula One team. Anybody know what this logo is? Avanade. Avanade do a lot of work together with Microsoft and high-profile customers working on those technologies. Now, those logos aren't on the card just for advertising. There is a strategic partnership between Avanade and Microsoft and the Lotus team to be able to actually develop technologies that helps Lotus to go motor racing. So what happens in Formula One is, if you've watched a race weekend, they go out and practice on Friday. Friday morning, Friday afternoon, they do practice. They harvest several gigabytes of this telemetry data. They have to get their cars set up Saturday lunchtime before they go into qualifying. So you look at scenarios where, how do you process and do lots and lots of complex processing on several gigabytes of numerical data, run it through all of these physics models to actually decide what setup you're going to do for your car on the Saturday. And having a technology that allows you to spin up hundreds or thousands of actual servers for 24 hours to actually process and churn through this data, and then just take the servers away when you don't need them, is going to be a really, really compelling technology. Now, there isn't much public knowledge about what goes on in these types of projects. There are press releases from Microsoft and from the Lotus team about how they're collaborating together, but the Formula One teams are fiercely competitive, so they don't go into much detail about what goes on under the scenes. But you can imagine how cloud-based technology, is going to help an industry like Formula One. Also, onto the Internet of Things. This is something that a lot of people have been talking about. A couple of news stories that came out this year. First one is that CocaCola has stockpiled 16 million network IDs. So in a computer, if you have a network card, the network card has a unique ID. So why has Coca-Cola stockpiled 16 million network IDs? And what people are saying is to do with the Internet of Things. The soda machines that they're putting in restaurants like McDonald's, Burger King, all that type of thing, are going to have networks in them. They're going to be connected to a wireless network. Telemetry data is going to be sent from these machines to some kind of back-end service. And that's going to allow the service engineers to be able to, instead of going out to a restaurant and servicing all of the Coke machines, once every month, maybe this machine is going to get, 5 times more usage than this machine because it's in a different location in the restaurant. This machine will be able to send alerts, statistics about how many cups of Coke it's poured. Also, if anything's going wrong with that machine, it will be able to provide an alert. So the service engineer can go into a particular restaurant to a particular machine because it's reporting a problem using wireless technology. And they've also got the telemetry data, the statistical data about how well the drinks are selling, how well the drinks are being distributed, and so on, which is going to be very, very useful to a company like Coca-Cola. Also, the smart devices, Coca-Cola spending $3.2 billion, Google spending $3.2 billion on a smart thermostat company, being able to actually connect up these devices to the internet. And there's some real scenarios where this is going to be needed. So many devices now have the option to be connected to the internet. You think about telemetry and think about cars. Think about a van delivery company. It would be great if a van delivery company can monitor all of the stuff about where their vans are going. They can monitor the engine temperature in real time, so they can radio a driver and say, okay, you've got issues with your engine. You need to come in. We'll give you a new van and we'll fix this van, because if you don't change it, then the engine's going to blow up in 50 or 100 kilometers or so on. And this is the same type of technology that has evolved in the Formula One industry. It's now coming into the consumer industry. So many devices like the cola machines, information display boards, advertising boards, weather stations, air conditioning, cooling, refrigerators, coffee machines at work, and so on, being able to monitor the conditions of coffee machines is going to be a growth industry for the Internet of Things. And I see cloud-based technology being a major factor in being able to enable the Internet of Things. We've got technologies like the Windows Azure Service Bus, which allows communication between these devices. We've got technologies like Windows Azure Storage, with table storage allowing us to store billions of entities in a storage table very, very cost effectively, and also allow for rapid querying on that data. So I see cloud and the Internet of Things as being two technologies that are definitely going to go well on each other. And this is a scenario where it's going to be useful. Think about how things are working with the electricity and the electricity grid. We've got relatives who live in Söder Ängby towards Nockeby, the posh area of town where all the big houses are. The latest trend over there is to get rid of all oil-fired and gas-fired heating systems and put in these heat exchange units that are powered by electricity, where they drill down into the ground and they've got these heat exchanging units. So over the year, everybody started putting in these heat exchange units, and then one day it got to -20. Everybody cranked up their heat exchange units, and the power went off to this big area in Södertälje. So what the electricity companies are looking at now is they're saying, well, we don't have enough power to power all of the devices. Wouldn't it be better to turn down everybody's heating by 10%? And be able to actually have control over that, rather than the entire block losing electricity. And think about what the next big trend is going to be now for the people in that area. It's going to be plug-in hybrid cars. So you come home, you plug in your hybrid car, you turn up your heating, you put the TV on, and turn on the oven and turn on the lights. That's going to be a lot of power. So you plug in your hybrid car, maybe you're not going to use it until 8 o'clock the next morning. So wouldn't it be better to charge the hybrid car at 2 o'clock in the morning, when not that many more people are using electricity? So being able to have more control over devices and to be able to centralize that control with the electricity company, to be able to actually have some power and influence and send commands to those devices, is going to be a very compelling technology. So this is what we do at Active Solution on Wednesday afternoon. We've got this learning by doing scenario. What this is here is a Pi brick. It's a Raspberry Pi computer which is connected to an Arduino device that has been modified to power Lego Mindstorm motors and take data in from Lego Mindstorm sensors. The Raspberry Pi runs Linux, and there are libraries available that you can put onto the Raspberry Pi that will allow it to actually send data to the Windows Azure Service Bus using the AMQP technology, and also make HTTP requests to the Windows Azure Storage Service. So that thing there is a wireless network card. So this device is now wirelessly connected. And one of the projects we're looking at is building an actual robot that we can control through the Windows Azure Service Bus that's going to be feeding back telemetry data, maybe with a camera on it, so you can actually control and see where it is, and actually get that device working. So one of these costs about 250 krona for a Raspberry Pi. So the price, for getting started in these Internet of Things projects is very, very low. Also, it's perfect for hobby developers. So if you like coding on a weekend and coding in the evenings, this is just pocket money that you're spending on these types of devices, and you can have a lot of fun with this technology and build some really creative ideas. This is our coffee machine. We're running condition monitoring on the coffee machine. Each one of these has a weighing scales underneath it. And that's another Raspberry Pi that's connected to the internet. I don't know if, it's actually connected to the internet there. We've got well, it might be actually a wired connection. I'm not sure exactly how that works. But what we're doing is we're basically monitoring the weight of the coffee machines. So when the coffee machine runs out of coffee, somebody can go and actually fill that machine. It is a fun project, but this has serious implications. Think about a company that has got 2,000 coffee machines out with customers throughout Stockholm. If they can internet enable those devices for a few hundred krona to be able to send telemetry data back when they need servicing, they've got a great scenario for being able to really make it more efficient. Somebody turns up to fix your coffee machine, the day before it breaks. That's going to be a great way to make it more efficient for the service engineers to do their jobs. Another scenario of using a Raspberry Pi, again this is Clemens Vastas on Channel 9, who's actually taking telemetry data out of his Audi, connecting, I can't remember the name of the interface, but there's an interface in the car which you can buy an adapter, and that connects to the USB interface of a Raspberry Pi. And he's written some code that he's published on GitHub that will take the telemetry data from the car, send that telemetry data into Windows Azure. So when he gets home, he can go and basically see all of the actual, the speed, the temperature, and all of the various parameters that are coming out of the car engine. That's being tracked into Windows Azure table storage, and it's using the Windows Azure Service Bus to communicate that technology there. So when you're dealing with telemetry, there's several information exchange patterns that we're going to be interested in. This is dealing with the Internet of Things. First one is telemetry. Telemetry is information that's coming from the actual device going into the actual monitoring system, which could be hosted in Windows Azure. So for a car, this is things like your speed, your engine temperature, all this type of stuff. A heating system, it's going to be what the temperature is the heating system on and off, how much power we're burning, and so on. We've then got inquiries. You've got an air conditioning system. You've set your air conditioning system to come on, so your house is going to be cool in the evening. However, Wouldn't it be great if the air conditioning system could actually ping out and get a weather forecast and then use that weather forecast data to decide whether it actually needs to turn on before you come home? If it's forecast to be a cold evening, then there's no point in cooling the house if it's going to be cold outside that evening. So weather services could provide heating and cooling systems with information that they need to do their processing. Commands. Your friends ring you up and say you're going to go out and watch a football game at O'Leary's instead of actually going home to your house. You want to be able to tell your heating system, don't turn on for another few hours because I'm not going to be home until midnight or 2 o'clock in the morning. Being able to actually have command and control over the actual systems. Then you've also got notifications, which is being able to provide the device or a range of devices with information about something that has happened. Maybe there's a new software update, or it could be broadcasting weather information rather than the actual system doing a request response to actually retrieve that weather information. So on to Red Dog Racing. If you've seen any of my demos where I'm doing things like animation and connect and stuff, I kind of like to have a hobby project that I use to demonstrate how stuff works in Windows Azure. Red Dog Racing is an adaptation of a sample called XNA Racer, which runs on the XNA toolkit. The reason it's called Red Dog Racing is Red Bull Racing is one of the Formula 1 teams, and Red Dog was the original code name for Windows Azure. So because I'm using a lot of Azure technology, that's why I chose that name. I'm really into Windows Azure. I like seeing how the Azure technologies and services can be used in many different scenarios and applications. So I like to work on stuff where I've got a good focus on Azure. I was kind of the physics geek at school, so this stuff really interests me. Dealing with vectors, dealing with angles, sines, cosines, frictions, momentum, velocity, the laws of motion and all this type of stuff. That's kind of stuff that really switched me on at school, and I was tended to be naturally very good at. So it's great to be able to use that the stuff I learnt in school in a project as well. Formula 1 is what I watch on the weekends. I'm really into the watching the racing, and also into the technology that's going on behind it. So anything that's related to telemetry and how that technology works is useful. I love driving games as well. I've mostly been playing Forza Horizon at home, and I really like the way that they're written. I like the way the physics works. I think they're fun to play. So something that combines all of this stuff together is useful to be working on. So what I've done is on the XNA platform, which is now deprecated by Microsoft, unfortunately, we do have a sample which is called XNA Racer. I've taken that sample and I've done some heavy customization to it. I've rewritten the physics engine completely. I've redesigned all of the tracks. As you can see, I've actually put different skins on the cars. I've added a kinetic energy recovery system, a curse system, and a DRS system, a drag reduction system. And I've also done integration between the actual game and Windows Azure. So we've got the actual, sorry, that slide needs updating due to the branding change. It's, I won't bother doing it now. It's, I've been running through all my slide decks and changing everything to Microsoft Azure because of this branding change. So we do have the integration there between the actual game and Microsoft Azure, and I'm using various services in Azure to actually run and power the game. So I'll just show you a bit about the game development. I do have another session on gaming physics, but this is kind of fun. This is when I was rewriting the physics engine when I didn't really know what I was doing. This is with the car stationary on the track with no external forces running on the car. This is when I was working on collision detection and trying to get a realistic collision between the car and the road. And then also try and make it realistic so when the cars crashed into the barriers they would bounce off. I was a Dukes of Hazzard fan when I was a kid, so I really wanted to have jumping in the game, and I wanted to have quite a realistic way that the car would land from a jump. And there it's kind of looking more like a trampoline running off the road there. And then the game actually has loops in it. So one of the actual most complex things was to actually get the physics right when a car goes around the loop. And this was my first attempt at it. The impressive thing here is that the car actually reaches 45 times the speed of sound when I actually looked at the telemetry data. You can see the MPH is just going crazy there. But I kind of... after that, I got a bit discouraged, and I spent Christmas, sort of Christmas Eve and Christmas Day and Boxing Day, as we call it, annandag jul in Swedish, sat with a pen and paper, just basically drawing lines and vectors, and figuring out what happens when the car goes around a corner. What effects do we have for gravity, downforce, centrifugal force, tire slip? One of the things when I rewrote this physics engine, I decided not to look at anybody else's code and not to actually use sort of sample physics engines that you had on the net. I wanted to do build it myself from the physics I learnt at school when I was 15 years old. There's still a couple of glitches in it, but it is actually working quite a bit better than it was previously. So back to the cloud stuff. When you're developing an application for Windows Azure, looking at the Microsoft Azure platform, what you'll notice is that there is a large number of services. And if you watch the build conference, you'll also be aware that the number of services that we've got on this platform is increasing. New services are coming out. Also, all of these services are evolving and changing and having new features added to them. So the real challenge that I find when looking at how we implement something in the cloud using Azure technologies is, which technologies are we going to use? How are we going to store our data? Are we going to use table storage, or are we going to use Azure SQL database? Do we need a big data scenario? If we need queuing technology, are we going to use the service bus, or are we going to use storage queues to be able to actually handle those types of messages and so on? So there's many different challenges there, being able to actually select which services we're going to be working with. So what I did was I took the same information exchange patterns that we've got in the Internet of Things that Clemens Vastas has talked about and written articles about, and basically implemented them in the game. Telemetry was easy. We've got the timing data, so the driver details, the sector times and the lap times are basically sent into Windows Azure, and they're stored in Azure table storage. The laps basically have a sector every 500 meters. So on the smaller tracks, I think there's about 9 sectors, and there's maybe sort of 25 sectors on the larger tracks. So this means sort of every 10 seconds or so, we're sending a message onto the queue with the actual sector time data. And we can use that to actually, provide some kind of a live feed on how the drivers are driving around the track. And also this acts for the high scores. So you can see who's got the fastest lap time by running a query against table storage. Telemetry, that sends the car position, the driver input, and lots of parameters that we're getting from the physics engine. Telemetry data is sampled 10 times a second, and it's batched up into messages of around about 10 telemetry data points and sent every second. I thought sending it 10 times a second is going to put too much load on the queues. So we basically harvest about 10 samples and just send one message a second there. And that gives us fairly real-time data in the actual telemetry processing within the cloud, and it also gives us quite a lot of accuracy. If we sample anything less than 10 times a second, we don't really see the car's position accurately as it's actually going around a corner. We really want to have the driver input sampled a lot, the car's position sampled a lot. So that's the kind of scenario I came up with. Clemens Vastas, in his telemetry sample in his car, he's sampling once a second and sending up the messages once a minute to actually reduce the load on the service bus queue. So he's using the same techniques as me, only a much sort of a less frequent sampling rate. For inquiries, when you start the game will make a query into a REST service in Windows Azure, and it will get back the best lap times. So you can see down here we've got the actual lap times high score. It's a bit hard to see there, but you'll see it when I'm actually playing the game. And that's coming from the actual lap times that are stored in table storage from all of the players that have played the game. The replay data, we've got ghost cars in the game. The ghost cars are basically rendered from replay data from previous laps, and this is coming from blob storage. So when you start a lap, we make a query to the high scores table. We get the high scores for all of the actual laps that have been driven. We then actually go to blob storage and we download the replay data for the ghost cars. So when you actually start driving the lap, you'll see the ghost cars for all of the other people who've played that lap. You can't actually compete one-on-one against somebody else in the game because, to get the actual, real-time playability, that's going to be a challenge using Azure. All of the games use their own protocols for that type of stuff. But you can actually race against somebody else's previous lap with the ghost cars. And I find that kind of makes it very competitive and very easy to see when you've done a good line through a corner or a bad line through a corner, because you'll overtake ghost cars or ghost cars will overtake you. For commands, I haven't got this implemented, but I do actually do a workshop, or I'm going to be doing a workshop with this actual racing game. So the first thing I'd do if I was on one of these workshops and I had the source code for this game is I would basically double the engine power or reduce the mass of the car, so the car would be a lot faster. So I've got something called race control, which will basically monitor somebody who breaks the rules. So if the car goes faster than it can theoretically go, if I detect that in the telemetry data, I can actually send a punishment out to the actual drivers. And what I'm doing at the moment is I'm basically giving them a large amount of vertical velocity. So if somebody mods the physics engine, their car goes really, really fast, and 20 seconds later it just flies about sort of half a kilometre up into the air, because it's basically that cheating has been detected by the race control service. Notifications. This, I don't think it's working correctly because of the actual firewall in here, but I'm using the service bus using the events notification service to be able to actually send messages out to the other players in the game. So when a player completes a lap, a message comes up on the screen saying so-and-so has set such and such a time in the lap. So that's providing the notification patterns. The way I'm doing it using the net eventing relay service is not that scalable, so I'm going to switch to a different way of being able to do it. There's some new technologies coming out from the service bus build, or I might look at using something like SignalR to provide that kind of notification there. So I'll just basically run through a bit about the architecture, look at how the game is working. What we can see here is the various services I've chosen to use in the Azure platform. So starting off with the actual information that's coming in, I'm using the Windows Azure Service Bus. I've also got the option to use Windows Azure Storage Queues as well for queuing the data. So we have lap and telemetry data coming in from the actual drivers who are driving the laps. I have a worker role running in Windows Azure, which is basically listening and dequeuing this data, and it's then going over to storage services. So I'm using table storage to store the lap times and the driver telemetry. I'm using blob storage to store the driver replays data. That gives me fantastic scalability. I can store 200 terabytes of data in a Windows Azure storage account, and the tables are scalable, so that will allow me to have literally billions and billions of rows of telemetry data in the actual telemetry table, and also be able to query that telemetry data for a specific lap in a couple of hundred milliseconds. And that's going to be really important for building a game that you want to be scalable. I'm basically paying, fractions of a krona per month for the actual data that I've got stored in there. I could be storing the data for millions of players using exactly the same architecture. It will be costing me more per month, but I don't have to make that initial investment to actually provision all of the infrastructure. I just, if I've designed it well, then it will scale to be able to handle that type of load. I'm using websites, Azure websites, to actually display and provide the actual view on what's going on in the actual website and do the high score times in telemetry data. So as more people start playing the game, I can scale up the worker role tier, and I can do this dynamically to be able to actually process that telemetry data and lap data and get that data inserted into the storage services and so on. So this architecture, although this is a pet project and it's a game and it's fun and it's a nice way to think about using Azure, what I'm really interested in is you could take exactly the same architecture and you could use it for the Internet of Things. So why not just connect things to the actual service bus? If you've got a car or a product or a coffee machine or a mobile app or a soda machine sending messages to the service bus, it's pretty much the same pattern. You have a worker role that dequeues the data, puts it into some form of storage, and you have an actual website where people can actually go and view and monitor that telemetry data and be able to actually see what's going on in the different devices. So I'll basically show you how the game runs. I've got a couple of projects. This Red Dog Racing project is acting as the back end. So if I run this with Control F5, this is basically going to simulate the worker role running in Windows Azure. The reason I'm doing this is so we can actually see the data that's coming off the various queues and so on. So I had actually played the game before I ran this up, so you can see it is actually pulling lap and telemetry data off the actual queues, and it will be actually inserting those into the actual tables. What we see when we go into the website And this page, when it loads, will hopefully display the actual positions. Now I'm using the same scoring system as we use in Formula 1, so you get 25 points for first place in a lap and then 18, 15, 12 or whatever. So, you know, Alan's in first place there with 68 points. You can see the times that I've set on the beginner, the advanced and the expert track. So setting a good time in all three of the actual laps in the game, which should, you know, give you a good position in the game. We can then go into the different tracks. We can go into the beginner track and the advanced and the expert track and basically see the actual times that have been set. This data is coming from table storage. So if I go into the storage table, into the, I think I'm using, it's really a test project. It's really a proof of concept at the moment. So this test 02 lap times. We can basically see the table storage data that I'm storing in table storage there. So if I zoom in on this, what I'm doing here is I'm basically sorting or actually storing the data for each particular lap. So we have the level, which is 0, the car type. The amount of damage, it basically records as you crash into a barrier, you'll basically get damage added onto your car. So monitoring the amount of damage as well, storing that in there. We've got the lap ID, and then we've got the actual lap time in milliseconds, and we've got all of the sector times. Now, when I'm working with table storage, I'm really interested in showing the top lap times. So when you're querying table storage, it's not like SQL Server where you can do, you know, select, you know, top 10, you know, lap times, top 10 star from lap times where track equals track 1, and then do, you know, order by lap time. What we have to do in table storage is think about actually storing the data in the order that it is going to be queried. We don't have an order by clause in table storage queries. So what you can see here is I've got something called a partition key. The partition key is a way of being able to partition the data, or basically store all of the data in basically an ordered group. Now I'm using the track ID as the partition key. So track 0 is the partition key. It is very efficient to select all of the entities in a certain partition, or the top 10 or top 20 or top 100 entities in a partition. However, when I do that selection, I'm going to be getting the actual items coming in the order that they were stored in table storage. So if I query for everything in the track 0 partition, I'm going to get the data in this order. Now the row key is also a string, and the row key is basically going to govern, in my scenario, how the data is sorted. So the row key there is 0069085. If we go across and we look at the lap time, you can see that the lap time in milliseconds is 69085. And that's the fastest lap. The next fastest lap is 71141 and then 71851. And because I'm using a zero padded the zero padded lap time starting off with the row key, that basically means that when I query, I'm going to get the results coming in the right order. I've also added on a timestamp, which is when the lap was set. So, you know, there is a chance that two drivers are going to drive the same lap with exactly the same number of milliseconds. And the combination of partition key and row key needs to be unique. So I have to drop on something else there, which is a timestamp, which basically says, you know, how they have it, sort of when the actual lap was set. So we don't get those actual blocks coming in there. So onto the actual game itself. Hopefully the actual data will have been dequeued and put into the actual database itself. I'll see if I can fire up the game. Sorry, that was the wrong project there. So XNA, the XNA library, unfortunately it's been discontinued. I kind of think it's you know, one of the really nice things that Microsoft has developed. It allows hobby gamers to actually develop games. XNA sort of lives on in something called Monogame, which is an open source initiative using the XNA technology and basically based on the Mono.NET framework. So Monogame, you can build apps for a number of platforms. It targets not only Windows platforms, but also platforms like Apple, iPhone and so on. There is also another game development library, which is Unity, which also allows you to you know, build games for multiple platforms and devices. I kind of prefer Monogame because you're working a lot in Visual Studio. Unity has its own editor. It does also have a Visual Studio plugin. Both of those are free if you want to actually play around and experiment with that. The reason that I'm using XNA still is that this game sample has a lot of shaders which are written in a language called HLSL, High Level Shader Language, and I I can't get those to compile in monogame, so I might port it to monogame, but I do have to spend a weekend fooling around with HSL syntax, which I'm not too keen to do. Oh. So the audio is not that great in the game. I haven't rewritten it yet, so I'll just go in and play without audio. I'll drop in Alan Azure as the actual name there. And I'll just run around a lap. So things I've modded in this game, I kind of spent a long night in sort of an image editing thing, taking the actual skin, original skin for the car and taking the Windows Azure logo and just basically copy pasting in there. So we do have a Windows Azure car. I'll actually drop onto the middle lap actually, because that's a bit more exciting to drive. As I've rewritten the physics engine, the game previously didn't have the concept of gravity really, so you couldn't really do jumps in the game. So one of the things I really wanted to do is to make it fun to actually do the jumps. So I've put in a lot of sections where you can actually jump over other tracks, and I kind of wanted to have this one where you could actually jump through a loop of another track in the game. You can see the ghost cars here from the other players. So here I'm overtaking a ghost car. That will move me up at one position in the rankings there. Also, I've put in the concept of centrifugal force, so you will actually slide round corners. The previous game, you just rotated instead of steering. So if, as long as you were quick enough to actually turn the car, there wouldn't be any concept of tyre slip or centrifugal force. So I've basically put that into the game as well. I've rewritten and redesigned all the tracks. The track data was really easy. It's kind of like a 3D spline. So just modifying the 3D points in space allows the track will basically build itself based on that 3D spline. You can see here I'm using a DRS, this thing that's flashing on and off. DRS will reduce the actual downforce on the car, but also reduce reduce the downforce, but also reduce the aerodynamical drag. So the car will go a lot faster when you're using DRS, just like in Formula 1. But if I try to go around corner with DRS enabled, you can see it will just slide off and crash into the barrier. The KERS, you can see this thing lights up, and this will give me a boost, the kinetic energy recovery system. And then when I brake into the corner, it will basically charge up the KERS battery, and I'll be able to do what they call KERS harvesting in Formula 1. So I kind of wanted to put those two in to make it a bit more interesting, actually playing the game. So I think I'm fairly near the end of this lap. I do have quite a way to go, so what I will do, I'll just exit from this lap and not spend too much time playing the game. But what happens as the game is being played, what you can see in this actual application here is the telemetry data and the lap data being actually processed by this actual back-end service. This is simulating what will be going on in the worker role. The game is basically sending messages to the queue every few seconds, or for every 10 seconds for the actual lap data, every second for the telemetry data. And that's then being dequeued and inserted into these actual storage tables in Azure. So if you look at the another of the tables for the telemetry data, you can basically see what sort of stuff I'm storing here. The lap data will basically contain the lap data will contain one row for every lap that's driven in the game. The telemetry data will contain up to 1,000 rows. So if you're driving a lap for 100 seconds, there's going to be 1,000 rows of data in that telemetry table. So there's going to be a lot of data here. And we're capturing a lot of stuff about the driving game. If I just zoom in on here, we can see what's being captured. Again, I'm using table storage. Here, the partition key is a lap ID. So this is efficient when I select the telemetry data for a specific lap. I say, okay, give me all the telemetry data for this specific lap, and all of that stuff comes back. The row key is the lap time in milliseconds. So I ensure that these two are not going to get duplicate values. And I also ensure that when the actual telemetry data for specific laps comes back, all of that data is going to be in order of the actual millisecond in the lap when that data was written there. And then I've got, you can see I've got these the actual properties like the acceleration, the brakes, the car type, the X, Y, and Z position of the car, distance above ground if you're doing a jump, and then I've got things like downforce, drag, engine force, and if we scroll along here. there's a lateral force, lateral G's, lateral velocity, player name, and all these various things like that, the rolling friction. So I can build up a lot of complex analysis based on this telemetry data. And also, another thing about being able to store this data is we can actually use it during the game to actually assess how well we're playing the game. So if you go into the website, I can then go into one of the actual laps and click on the actual lap time. And what we're doing here is making a query into a REST service, which is basically returning the telemetry data for a specific lap. So this is basically an ASP.NET MVC application. The controls that I'm using here, it's the Flutter JavaScript graphing library, and I'm using JavaScript to actually make a query to a REST service, which brings back the telemetry data for this lab. And what we're seeing here is, and I've really just only started working on actually plotting this telemetry data, but being able to provide the driver with feedback about how well they've driven that lap. So here you can see the actual car speed. We had good acceleration here, and then we had a crash, and the speed dropped down, and you can see the car speed throughout the lap. Here we can see the driver input. So what we're seeing here is the throttle. You can see the difference between using the throttle and using the brakes here. We've got the DRS, the drag reduction system, when that was being applied during the laps. We've got KERS, when the kinetic energy recovery system was being used. And then we've got the percentage KERS battery here. So when the actual brakes go on, you can see that the KERS battery is increasing, and then I'm using the throttle and KERS to actually give the car speed during the lap. So what I plan to do to enhance this is to allow it to do lap time comparisons. So that was the best lap. However, if I go back and look at one of the previous laps, I want to be able to compare this telemetry data with the leading telemetry data, and you'll be able to see the differences in speed, but also see the differences in driver input. Why is your friend faster than you at doing this driving game? When are they using the throttle? When are they using the brakes? When are they using KERS and DRS? And be able to do those types of comparisons there. So that's one of the things I'm focusing on looking at now to actually improve how the actual driver telemetry data is going to work. So this is how it works for lap time and scoring. We're basically putting messages onto the service bus. These are being put into the lap times table, and the website is able to display this information. I've run through how that actually looks in table storage. Telemetry processing is the same thing. We're just sending a lot more data, a lot more properties about the car. Again, that's going into to table storage. And we're able to actually, do different things with the telemetry data. Another thing that I've built that I haven't demoed, I haven't got this running right now, is a telemetry analysis application. So this is a Windows Presentation Foundation application that is allowed to, which can basically go to, say, the top 100 laps, and you can download all of the telemetry data for the top 100 laps. And then you can actually plot out the car's position. It's quite hard to see, but I'm using different colours for the speed. So it's green when the car is going faster. It's a darker red when the car is slowing down around corners. And then this is indicating where crashes have occurred within the actual lap. So here you can see the telemetry data from multiple drivers. And I want to add functionality so you can zoom into a corner and see the different lines that people have taken around the corner, and what's a fast line to drive around that corner, what's a slow line to drive around the corner. You can do all that sort of stuff with this. And this is just game data. Imagine what you could do by looking at the telemetry data for your van delivery company, plotting that on a map and seeing where all your delivery vans are and where they drove during the past week. Were you efficiently being able to actually deliver all of the actual goods? Are there people getting stuck in traffic jams? Are there people who are breaking the speed limit? Are there people who are taking 2 hours off and just sitting in a cafe and so on? So being able to monitor all of that stuff for a real world scenario is going to be another great way to use this type of technology. The replay and the ghost cars, there's basically two thoughts behind telemetry data. One is to do real-time telemetry, whereby during the game, every second, you're going to be sending this data into the cloud. Now, with millions of players, that's going to put a lot of load on the actual queue service. So another way of thinking about telemetry data is wait until the end of the lap and just send a big blob of telemetry data for that specific lap and store that as one actual unit of data. So the driver replays is another way of storing telemetry data. It's stored in blob storage. We should be able to see the actual blobs here in the actual account. And it's basically binary data which contains the driver's position sampled 5 times a second throughout the lap. So if I go to the Red Dog test storage account, if I go into the replays blob container, You can see all of these various blobs. So each one is about 30 or 40 kilobytes, sometimes 50 kilobytes, depending how much data. So that's a binary blob of data that contains the car's position, the car's direction, the car's up vector. And it also contains stuff like the sector times and so on. So when the application starts, we're going to the lap times data, we're querying for the top 20 lap times or so on. We get that back and then we go out to blob storage and we query for the actual blobs based on the lap ID of these fastest lap times. We download those blobs, and in the rendering engine, we're actually using the telemetry data from the actual replays blob from this binary data to actually render the ghost cars on the screen. Now, I didn't write all of that. The original XNA game basically had the functionality that when a lap was completed, if it was the fastest lap time, it would save this blob down onto the storage system. So that would be a file storage, or it would be the Xbox storage if you're running on an Xbox. So all I did was modified the code. So instead of saving it onto the file system, it basically saved it into blob storage. And it did it for every lap that was completed, not just the fastest lap. And then I just rewrote the code for rendering the ghost cars. So instead of there just being one ghost car, there was an array of ghost cars that was basically driven from this actual stuff in the replay storage. So as you can tell, I've got quite a bit of sort of free time on my hands to do this stuff. I was at the MVP Summit in November, and I kind of had European jet lag, so I was waking up at 3 o'clock in the morning with nothing to do. So I kind of had about sort of 4 or 5 hours a day to actually do coding before breakfast, and that's when I got a lot of stuff on this game built. Yeah, so that's basically what's happening with storing the actual ghost car data in blob storage. It's easy to do this, it's very efficient to do this, it's very cost effective and very performant to use blob storage for that. The in-game messaging, as I mentioned, I'm using the relay service eventing. It's not the best way, not the most scalable way to do things because it will only scale up to 20 clients. But basically what happens is we have an endpoint created on each one of the services. We're sending in our lap time and telemetry data, and when the lap time processing in the actual worker role determines that a lap has been completed, it sends a message to the relay eventing service, and that message is broadcast to all of the players of the game, and that just basically pops up saying Alan's got this lap time. So if I'm doing one of these Azure racing game workshops and I've got 16 people in the room playing the game, this is going to be fantastic. If we're doing the Global Windows Azure Bootcamp and we've got 5,000 people playing the game around the world, this isn't going to scale. So I'm going to maybe look at using a different technique for this, maybe Signal R to actually broadcast those messages and do something a bit more scalable. So just to round off, a couple of pointers. If you're interested in game physics, I kind of think it's really addictive, it's fun, but unfortunately I'm not good enough to get paid for doing it, so it's kind of like a hobby. But I did actually kind of just for fun, I sent in a session description on game and simulator physics for developers, gamers and petrol heads, which is going to be a fun session looking at how I built the driving physics game engine. To my complete surprise, they've actually chosen to present that session at Tech Days in the Netherlands. I have not done that much preparation for it. I did one for the .NET user group a few weeks ago, and they seem to be more interested in that than they were interested in Windows Azure. But I know you're not going to make it to The Hague next week, but that session will be recorded and it will become online. So if you do want to actually look at that one, I'm also doing this session again, so that will be recorded and that one will be put online. So if you do think physics is fun like I do, that might be worth watching. Also, the racing game workshops, I'm scheduling at conferences, so NDC in Oslo, we're running the racing game workshop. We're also running it at DevSum in Stockholm. And then for the Sweden Azure user group, I was thinking it'd be good fun to do it on a Saturday and just invite people to come in and actually spend a day playing around with this. So the idea is it's focused on learning about Windows Azure, but the labs are going to be you get the driving game not connected to Azure, and you basically connect the driving game to actually upload the ghost cars, download the ghost cars, send the telemetry data, send the lap times, and then the fun part is when you complete the lab, you're competing against the other people in the workshop to actually set fast lap times. So that stuff should be good fun if you're interested in that. So thanks very much for listening. Hope you've enjoyed the day at the conference. I will be around for another sort of few minutes if anybody does want to talk about gaming or Windows Azure or Formula One or car physics or anything like that. Thanks very much. I hope you've had a good day.